Hello friends, welcome to our YouTube channel GIL Qubit Minds. So in this session I will discuss on quantum computing. So this is our video 2. So I would recommend first you go through our first video, introduction video of quantum computing, then you can come in this video. So here first topic is qubit. We know that it is a quantum bit. It is the fundamental unit of information in quantum computer. Okay. So like in classical computer we are using bits 0 and 1. Here we are using 0-ket and 1-ket, like this. Okay, these are all qubits. So qubits also follow some properties. So when we work on qubits, so we can see that we have to take it in superposition. So qubit can be a combine of both 0 and 1 simultaneously, which allows the quantum computers to perform many calculations at once. So this is superposition. We'll also explain this in this later video. Now next property is entanglement. It is a very important property also. When two qubits are entangled, the state of one qubit is directly related to the state of another, no matter how far they are in same continent or same country or different country. So they are entangled. Two qubits are entangled each other. This property is crucial for quantum computing power. So it is very important feature of quantum computing. And another feature is quantum interference. So if we carefully control the qubits in any quantum algorithm, we can enhance the probability to get the correct answers, and we can cancel out the incorrect ones. So this is the way we do quantum interference. So quantum interference help us to cancel out the incorrect, and it increase the probability to get the correct answer. Okay. Now we will first understand about the Hilbert space. So we have already know that what is a vector. Vector has, in physics we have used as, it has a magnitude and direction. So here in quantum computing we are using this vector as, this is row vector, the column vector, and this is row vector. Okay, now it is little bit different than a vector space. So if we know the vector space consists of lots of vectors are inside the vector space, but here it is little bit different. It is a complex number vector will live in this vector space. So when complex number vector is living in the vector space, we are calling it as a Hilbert space. So it can scale, it can multiply, divide, everything it will happen in the Hilbert space. So it is named of it has been named from researcher David Hilbert. So here we can see addition, all the operations we can consider: addition, multiplication by scalars, complex conjugate. If the number is this, we can, the conjugate will be, it is plus, it will be transferred to minus, a minus b, it is the conjugate. So also we can derive the magnitude as well with this modulo of a plus b I is the imaginary part. So this way the vector can be expressed: 1 plus I, 2 minus I, 3 plus 2I, like this. Okay, well, now in next slide we are coming to Dirac notation. So how we are going to express a qubit? So with this notation we are going to express. So it has been introduced by Paul Dirac. So we are expressing the qubit it describes the quantum states, the operator, and its products, inner products, outer products. It is describing it. So a Ket represents a quantum state vector in a Hilbert space. So Ket is a column vector and Bra is a Hermitian conjugate, means the complex conjugate transpose of Ket. So here we can see, so if 0 Ket is 1 0 column vector and 0 Bra will be the complex conjugate, means the dagger symbol is there. Ket 0 Ket dagger is the Bra 0, means it will be transposed 1 0. So it will be transposed this way. Similar for 1 Ket as well, it will be for 1 Bra, it will be transposed here. It is a conjugate transpose. So for Bra it will be row vector. Now here this is general form. So here we will see this is the standard basis form. So in this standard basis form we are multiplying alpha with 0 Ket and beta with 1 Ket. So this alpha and beta is it is a complex number. So we can call it as a probabilistic amplitude or complex coefficient also. So the main thing is that it will follow this rule, this normalized rule, alpha square mod plus beta square mod equal to 1 for classical state of 0 and 1. So here now we will come how this 0 Ket is deriving 1 and 0, how it is getting formed. So there is a rule. So if this is the set, classical set 0 and 1, whenever we find out this element in the set, we'll put it a 1. Other, if you don't find out, then we'll put it a 0. So here 0 Ket, if you consider, so the first element is 0, so we'll consider 1. Second element is 1, we'll make it 0. For 1 Ket, the first element we are taking, it is 0, not 1, so it will be 0 here. And for second element 1, we find it out, so it will be 1. The rule, if the element is found, then 1, else 0. Similar, if you take another example, A Ket equal to 1 0 0. How it is happened? Because the set we have considered A, B, C. The first element is A, so it's 1. Rest element is B and C, so it is 0 and 0. Similarly for B, it is 0. First element is 0, then 1 0. C is 0 0 1. So depending upon when we are comparing with the position where this element is, we found it out. So similar for Bra also, it will just reverse complex conjugate. Okay, now here we can see one if alpha equal to 1 by root 2 and beta equal to 1 by root 2, what will happen? So we can say this alpha square, the alpha, if you want to get the probability of getting 0 as an output, 0 Ket, what is the probability of 0 Ket to be in output when we measure it or observe it? So the probability we can say alpha square. For getting 1 is beta square. Okay, so if we want to get the probability, then 0 probability of 0 Ket is 1 by root 2 whole square equal to half. Same, this is also half, means this is a 50-50 chance of getting 0 and 1. So we call it as it is in a superposition. The state is in a superposition state. Okay. Okay, now we'll check how we'll do inner product and outer product. So here we can see inner product is Bra-Ket pairing, means we are multiplying this to Bra is phi Bra and Xi Bra and phi Ket. So if we are replaced with 0 and 1, if we see that the word set is 0 and 1 set, classical set, then we'll see that 0 0 1 0 1. If you multiply 0 and 1, it will be 0 1 and 0 0 1 1 1. So here we can see, observe that whenever we are multiplying, we are getting a scalar element. So it is a scalar complex number as an outcome. For Bra-Ket, you will always get a scalar number. But for other, when we will see here, when we are doing reverse means Ket with Bra pairing, then we will always get a matrix, not rather than a scalar. Okay. So now we will check here if 0 and 1. First we will check this one, 0 and 1, how it is getting multiplied. It will convert it into a vector. This is Bra, so it will be a row vector 1 and 0. 0 Ket means 1, and this is column vector 1 and 0. So now we are multiplying each other as simple matrix multiplication, then we are getting 1. So the main formula is here. So if I generalize this one, x and y, by replacing any term a and b and c and d, then this will be the output, a, c and b, d. For outer product, we are getting xi Ket and phi Bra. If we multiply, we are getting a matrix multiplication. Why? Because here is a 2 by 1 vector. We are multiplying with 1 by 1 row 2 column vector. So by default the resultant matrix will be 2 into 2 matrix. Okay. Now here we can see when you are multiplying it, so it will be like this way. So the basic, if we generalize this one with a and b, c and d, then the first element will be ac, then ad, then bc and bd. So this will be the final output. Okay. So we can say that this is a this for inner product a, this 0 and Ket 0 and Ket 1 is orthonormal. Why we are saying orthonormal? Because it is satisfying two properties. One, orthogonal property means it is perpendicular and normalized. So why orthogonal? If Ket, Bra, I, and when we are doing inner product of vector j, if it is result is 0, when I not equal to j, then we'll say it as a orthogonal. So if you say it here, if you see it here, 0 1, it is result is scalar 0, 1 0, it is also 0. So it is saying as a orthogonal. For normalized, when the self I, when we do inner product with the same vector, it should give us the result of 1. So here we can see 0, inner product is 0, then we are getting 0 1, here also 1 1, we are getting 1. So it is a normalized. So we are saying together orthonormal. Okay. Now coming to Bloch sphere. So this is, we have seen the so previously we are just working with the standard basis form of a qubit state. Now we will see in a geometric representation how it is just a geometry for our understanding purpose. We map it here like this, Bloch sphere. So it will visually, it will more means help us to understand the state. So initially we are writing it here. If this is a arbitrary position xi alpha 0 bit, this is the probability I have said. So alpha square is the probability of 0 Ket and beta square is the probability of 1 Ket, where alpha and beta are the complex number. Now we are transforming this presentation into a polar representation, means we are changing into geometry angles. So when this theta is a polar angle, so I think here this is the theta. Okay, so phi Ket equal to cos theta by 2 of 0 ket, and e to the power I phi sin theta 1 ket is the representation, polar representation of this same basis form, standard basis form. Now we know that Euler formula is this, if e to the power I phi, so we can replace it with this term, cos phi plus I sin phi, and it is same sin theta by 2 of 1. Okay, so we'll see later why we are multiplying this element only with the second one, not with the whole statement. We are only taking partial. Okay, not we are multiplying the whole state. Okay, so this is the main formula where theta is the polar angle. It determines the probability of measuring 0 and 1. Means here you can see this is a sphere, this is the y, this is z, and this is minus z. So here we'll see this is qubit 0 and this is qubit 1, and here is x minus y minus. Okay, we'll see also azimuthal angle, the phase difference between 0 and 1. So theta is responsible for, this is the total theta is responsible for from turning from 0 to 1, and we will see the azimuthal phi also there, which is responsible for rotating towards the axis. So x and y is the phase information, and z determines how close the state to 0 and 1. Now here is the complete diagram. Here we can see this is the theta that we have said is the polar angle, is the probability distribution between 0 and 1. Okay, so this is the total is theta. So it is actually says us what is the probability for getting 0 and what is the probability for getting 1. What is the distribution? It is mainly explaining us. What is phi? Phi is this angle. Suppose this is a point, this is state, quantum state here. So if you want to explain it to phi, then we need the help of this azimuthal angle. Determines the state lies on xy plane. In xy plane where this state lies, it will say it to us. So if we correspond x-axis representation, we can see this is the x-axis plus ket. So it will, on x-axis we will get this represented 0 ket plus 1 ket by root over 2. So this is the equator of this sphere, you can call it. Okay, where phi here, if the phi becomes 0, means it will lie on this x-axis, and if this theta is 90 degree, it will directly fall on this equator. It will be positioned here, and if on left side of the x-axis, then it will be 0 ket minus 1. The phase angle is getting changed here, it is minus. So it will, the phi will be 180 degree, means pi, and it will locate here on this minus x. If you are representing with the y-axis representation, okay, then it will, when we are representing with y-axis, then it is, we are representing the imaginary phase. When we are doing the superposition, we are doing this x-axis. So here we can see y, if it is plus y, then 0 plus I, there is a imaginary part is been covered here, and if it is minus, then it is just this phase is getting negative. So here we can see if the pi by 2, phi is pi by 2, means this phi is 90 degree, then we can write this expression. so it will be on y-axis. If it is minus, means minus pi by 2 or 3 pi by 2, and theta is 90 degree, then it will lie on y-axis. Okay, well, now going to next slide. So for Bloch sphere, we have seen that two types of phase changes. One is global phase changes, which is unobservable. So that in the initial video we have said that why we are multiplying with only this part ei with sin theta, not with 0, because there is two phase. Here x and y axis plays the phase change role, and z is playing the 0 and 1 role, probability role. Okay, so for the global change, if we are applying global change, then we cannot observe this one. The global phase change applies to the same factor to the entire quantum state. So if I multiply with this to this state, then it is multiplying with the entire quantum state. This does not change the measurement of probabilities, is considered physically unobservable, so there it will be no impact, we cannot see anything. But if we called partial or relative phase change, then we can observe it. So here we are only multiplying with this part, then this phase changes alter the quantum state on Bloch sphere and affecting the interference in quantum algorithm. When we will use this in the quantum algorithm, this will influence the interference. So if the same phase, the higher probability, means if the same phase, suppose this is both positive and positive phase we are considering, then it will be constructive interference. When the phase is one positive, one negative, then the opposite phase will cancel out and it will be destructive interference. Okay, so in the next session I will also add some more maths to understand this. Okay, in the next video I will add multiple Bra-Ket notation with multiple qubits, and I will start the quantum different kind of quantum gates. Hope you like this video. Thank you for listening. Please share and subscribe my channel, and if you find it helpful, please like this video. Thank you very much. Bye.